everyone. In this video, we're going to continue to talk about polynomial division. Specifically, we'll use synthetic division. Okay, number one says if x plus 3 is a 0 or a root, then find the other roots of x to the fourth minus 2x squared minus 63. So first and foremost, if x plus 3 is the 0, that means the actual x-intercept, if you solve for that, is negative 3. So negative 3 will be our quote-unquote box number up here. Okay, then I'm going to list my coefficients. So we have 1x to the fourth. Now, something that's going to come up in this problem that's different than other problems is going back to the definition of polynomials. So if you have a polynomial that's x to the fourth, there should be an x to the fourth. Then it goes in descending order, x third, x squared, x, and then x to the 0 would be like some number, a constant. And in this case, we have an x to the fourth, and then it jumps to x squared. And anytime it does that in synthetic division, you need to put a placeholder for the term that's missing. So how many x to the thirds do I have? I actually have 0 x to the thirds. And then I have negative 2x squareds. And I have 0 x's. And then I have negative 63x to the 0, but x to the 0 is just 1. So this is something that's slightly different than the other problems, is that you're missing these terms. You need to put a placeholder so the division works properly. We can talk about why that is more in class. Or better yet, see if you can figure out why you need that. Go back to long division. You might be able to figure it out. Okay, so we're first going to bring down our first number. You multiply with the box number. So 1 times 3 is 3. Then you add down the columns. And then you repeat the process. You multiply and then you add down the columns. So on and so forth. So if you do this correctly, you should have no remainder. So again, think about why that is. If you know x plus 3 is a 0, you know it's a factor of this polynomial here. And if it's a factor, it should divide in evenly with no remainder. Okay, so this is now my remainder. And then we go in ascending order. So it's my constant, my x squared, my x to the third. So then I would get x to the third plus 3x squared plus 7x plus 21 with no remainder. Okay, so now you've made this a third degree polynomial instead of a fourth degree. So we can then go ahead and find the others by either doing synthetic division again, but we don't know another root. So maybe we can try and factor. And if you have 4 terms, go through the factoring flow chart, we'd have to factor by grouping. So I'll group those two together there. And I can factor out a greatest common factor here, which is going to be x squared. If you pull in x squared times x would give me x to the third. And then I would need a plus 3. So x squared times 3 is going to give me 3x squared. My greatest common factor here is going to be 7. So pull that out. You'll have this. And if done correctly, your factor by grouping, factors should match. So then you can rearrange this and write it in a more simple form where you're talking about only products. So x squared is being multiplied by x plus 3. 7 is also being multiplied by x plus 3. So I'm going to rewrite x plus 3 once, and then I know that x squared plus 7 is what's being multiplied by the x plus 3, right? We distribute both of these to each of those, and it's the same thing as writing it this way. So how does that help me find the other zeros? Well, now you know, let's see, x plus 3 is one of the zeros. These are my others. So I can say x plus 3 equals 0, which means x equals negative 3. And hey, look, that means that this negative 3 is a double 0. It's counted twice. It has a multiplicity of 2 because it's here and up here. And then I can say x squared plus 7 equals 0. So x squared equals negative 7. Square root both sides, and you will have imaginary zeros. So really this would be the square root of negative 7 is I root 7, plus or minus, because you're taking the square root. Okay, so my zeros then would be negative 3 with a multiplicity of 2. It's a double root. And then I would have plus or minus I root 7. If you prefer, you can write that as positive I root 7 and negative I root 7. Okay, so since this is a fourth degree polynomial, I should have 4 roots, which I do. Here's 1, 2, 3. This is double counted. So that's 2 zeros, which makes us have a total of 4. Okay, some things to think about. Next problem is a little bit different, but kind of an interesting thought. So one of my zeros or my roots is imaginary. So still solving the same way, Still taking the same steps as before. I know x equals 3i. Set this equal to 0. And I'm going to make 3i my box number this time. I'm going to do the same thing where I list up my coefficients, and the process isn't going to change just because my 0 is a imaginary number. Let's see what happens though. So like I said, the process isn't going to change, but I just want to warn you that it's not necessarily going to be pretty, and that's okay. Just remember that that's okay not to be pretty all the time. So it'll look like this. I multiply across, and then I add down the columns. So this is actually going to be a complex number, 5 plus 3i, negative 5 plus 3i. Okay, then you're going to multiply below the line with the box number, which might take a little bit more effort, but we can do it off to the side here. So I have 3i times negative 5 plus 3i, and you'll distribute that 3i, so you'll get negative 15i plus 9i squared, which I squared is negative 1, so this is really negative 15i minus 9. Okay, and we'll fill that back in up here. So it's negative 15i minus 9. Now I'm going to add down the column, and you can't combine imaginary numbers and real numbers, so my imaginary number is going to stay the same, but I can combine my real number with my real number. So I have 13 minus 9, which give me minus 4. And then you'll continue to repeat this process. So I'll do this times this, and so on and so forth. I'm actually going to pause the video and do some of this computation on my own, so you can do the computation on your own and just remember that process. So pause, and I'll come back with the answer. Okay, if done correctly, this is what you should get. And it actually winds up working nicely at the end where things start to cancel, and then there is a remainder of 0, which there should always be a remainder of 0, because if we're saying this is a root, that means it's a factor, that means it divides in evenly, which there would be nothing remaining. Okay, so it worked out nice at the end, although this is not nice here. So we need to think of what we can do next. Before we move on, I just want to reiterate the fact that this process did not change just because it was an imaginary root. Okay, but what is not necessarily going to change, but something you need to think about is the next step. So think back to when we first discovered imaginary roots. We were talking about the quadratic formula and how a parabola that looks like this would have no roots because it wouldn't intersect the x-axis. So that's how it had imaginary roots. So when we were solving for roots, we were solving for x-intercepts. One of the methods we did that was quadratic formula, which is x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. So you could have got a solution that was something like, I don't know, negative 1 plus or minus 4i, okay, when all is said and simplified. Now, what is important to note here is that you had two solutions. It's negative 1 plus 4i or negative 1 minus 4i. Okay, and this always happens when you're thinking about your roots. You'll have the same two terms but opposite signs because of that plus or minus. Okay, so with that said, anytime you have a complex root, they always come in pairs, conjugate pairs, complex conjugate pairs. So what that means for us is if x equals 3i is a root, then x equals negative 3i also has to be a root. And again, that goes back to the quadratic formula. It'll simplify to be the exact same thing with opposite signs in the middle. So if I had 3i as a root, negative 3i automatically we know is also a root. So before we rewrite, let's scroll back down. Before we rewrite this as a polynomial where you have the remainder constant, so on, that would be really ugly because our coefficients would be complex numbers. So what we want to do when we come to a situation like this is use our other root. So let's leave this as my line of coefficients and repeat the process of synthetic division and see what happens. So I know if I divide 3i, I get this, but let's also divide negative 3i and use it as my box number and see what happens. So we'll do a couple together and then I'll have you kind of finished off on your own. So first thing you'll do is bring down the 1. Okay. So 1 times negative 3i is going to give me negative 3i, and look what happens. Those cancel out, and I get a negative 5. And to repeat the process is negative 5 times negative 3 is 15i. Hey, look at that. Those cancel too. So I'm left with a negative 4. Actually, we'll just finish this together. So that gives me a, let's see, negative 4 times negative 3i is positive 12i. Wait, those don't cancel. I'm just going to say that's a signal to me that I did something wrong, and then I look up here and see that that should have been a negative 12. Okay, so if things don't work out nicely here, that's a key that you should go back and check your work. That gives me 0 as a remainder, so I don't need to continue dividing. So this is my remainder, my constant, my x squared. And with that said, I get a nice polynomial, which is x squared minus 5x minus 4. Okay, so although it didn't start off very nice, things worked out really well at the end. If you remember that imaginary numbers come in complex pairs, okay, or really solutions, some solutions will come in pairs. So another kind of solution that will come in pairs, let's say you had like 1 plus or minus root 3, then your solutions would be 1 plus root 3 and 1 minus root 3. So you can start to think about other combinations that will come in the same two terms with the opposite sign in the middle. Anywho, now that I've finished that, I can find all the other roots by trying to factor this. Although if you try and factor it, I can tell you right now it's not going to work. So if you want to find the rest of the solutions, you can always use the quadratic formula because that will work on any quadratic. And since this is an x squared, it's a quadratic. So I do x equals opposite b plus or minus a square root, blah, blah, blah. You can finish that off on your own. But for now, that's a review of how you do synthetic division with some interesting cases. One where you have complex number and you have to think about complex conjugate solutions, and one where you need to fill in the 0 coefficients to describe how many of those terms you have. Okay, so if you have any questions, please bring them to class. Otherwise, have a great rest of your night.